Swayam Prabha. Digital India. Educated India.
Now we will start deriving the Hooke's law. If you look at the first bullet, it lists all the assumptions we have discussed so far. Okay. It summarizes all the assumptions we have discussed so far. So, when I say Hooke's law, it is valid only under these assumptions. That is why we discussed, when we talk of a relationship between stress and strain, then assumptions have to be discussed. Hooke's law is such a relationship, and so this limits the scope of Hooke's law. Okay. So, what are the assumptions? Homogeneous properties are the same at any point. Now, we know what properties are. We have looked at 3 material properties: Young's modulus, shear modulus, Poisson ratio. Isotropic, at a point material properties are same in all directions, and linear, elastic, okay, solid. Elastic, a definite relationship between stress and strain. When I say stress and strain, applies both for normal stress, shear stress, and then normal strain, shear strain. Okay. And linear tells you the relationship between them, between the stress and strain is linear. Okay. Okay. And what we do is we consider a body subjected to a general 3-dimensional stress. What do I mean by that? I have a body subjected to normal stress along x direction and y direction and z direction. Okay. Now, for easy discussion, we will consider a 2-dimensional case, and that is what is shown here. We have a plate in the undeformed configuration before the force is being applied, before the stress is being applied, and the length of the sides are delta x and delta y. And the first figure, what is shown is, it is subjected to normal stress along x direction, tau xx, tau xx, and it is shown to be tensile here. Now, the changed length of the sides are also shown, 1 plus epsilon xx into delta x, and the length of along the y direction has changed to 1 plus epsilon yy into delta y. Okay. For this condition, there is elongation along the x axis. So, epsilon xx is greater than 0, there is contraction along the y axis. So, epsilon yy is less than 0. Now, what is shown in the second diagram is the same plate, okay, subjected to normal stress along y direction. Please note the point, we are subjecting the plate to both normal stress along x direction and normal stress along y direction. Okay. And so, what is shown here is, second figure shows the plate subjected to normal stress along y direction. Now, there is elongation along the y direction. So, the original length along y direction is delta y, the new length, increased length is 1 plus epsilon yy into delta y. Now, there is contraction along x axis, which is the perpendicular direction, and the original length is delta x and the new length is 1 plus epsilon x into delta x. So, for this condition, epsilon yy is greater than 0, elongation along y axis and contraction along x axis. So, epsilon x axis less than 0. Now, what is it the third figure represents? We are applying both the normal stresses together, okay. That is what is shown here. tau xx and then tau yy. We are applying both the tensile stresses together. The first figure shows the plate subjected to normal stress along x axis, second figure shows normal stress along y direction, third represents the plate subjected to normal stress along x direction and y direction. Now, if you let us say there is no normal stress along y direction momentarily, let us take there is no normal stress along y direction, then because of normal stress along x direction, what would be the normal strain along x direction? It is given by tau xx by e, that is this length tau xx by e. This would have been the, let us say, increase in length along x direction if the two dimension element has been subjected to normal stress along x direction only. But because there is normal stress along y direction, there is some decrease in length along the x direction, there is some negative or contraction along the x direction. What is that value? How do you find out that? Okay. For the normal stress along y direction, the relationship between connecting tau yy and epsilon yy is given by this equation, just like we had seen earlier for x direction. So, this relationship relates normal stress along y direction to normal strain along y direction by the Young's modulus. Remember, once again we have taken the same Young's modulus independent of direction because it is isotropic. I write that relationship for normal strain along y direction, epsilon yy is equal to tau yy by e. Now, my direction of stress is along y direction, so x becomes the perpendicular direction. So, how do we write normal strain along the perpendicular direction is minus nu times normal strain along the direction of stress. So, when we substitute for epsilon yy in terms of tau yy by e, we get the expression for normal strain along x direction due to normal stress along y direction. Is that okay? So, of course, this is to be negative, there is a decrease in length which is minus nu times tau yy by e. So, this contraction is nu tau yy by e. Okay. If there were no normal stress along y direction, this would have been the increase in length, but because there is normal stress along y direction, there is some contraction. So, the net increase in length is only so much, that is what is shown here. Okay. The total is shown here tau xx by e and the contraction because of tau yy is shown here, the net is shown here. Okay. So, in terms of equation that is shown geometrically, in terms of equation the let us call the effective normal strain along x direction is equal to tau xx by e. If there were no normal stress along y direction, only this would be the value, but because we had normal stress along y direction, it caused a contraction along the x direction which is minus nu tau yy by e, and so this two terms put together is the net normal strain along the x direction due to tau xx and tau yy. Is it okay? The first term represents contribution from tau xx, which is let us say which is elongation. Second term tells a contribution because of tau yy, which is contraction, and if you sum together you get the net normal strain. Okay. So, what is that we have done? We have considered a body subjected to all the three normal stresses. For the present case, we have considered only a two dimensional case subjected to only tau xx and tau yy, and seen what is the normal strain along x direction. Okay. Now, let us based on this let us discuss this table. What this table shows is that the column headings are the stresses, the normal stresses along x direction, y direction, z direction. What are the row headings? The normal strain along x direction, y direction and z direction. Let us take the first column. Okay. what is the first column? The direction of stress is x along the x axis, direction of strain epsilon x axis along the same x axis. How are they related? By simply tau xx by E. Now, for when the stress is along x direction, y and z are the perpendicular directions. How are they related? Minus nu times the epsilon xx value, that is why you have minus nu into epsilon xx, which is tau xx by E. Similarly, the strain along the z direction, which another perpendicular direction, is minus nu times epsilon xx, which is tau xx by E. So, what is the significance of the entries in the first column? You applied a normal stress along x direction, and the 3 rows represent normal strain along x direction, normal strain along y direction, and normal strain along z direction. This is what we have seen in the slide previous to the earlier slide. Okay. Similarly, if you apply normal stress along y direction, the normal strain along y direction is tau yy by E, because it is in the same direction as the stress. Now, the perpendicular directions are x and then z. How do you represent? Minus nu into epsilon yy. What is epsilon yy? Tau yy by E. Similarly, for the z direction, minus nu into epsilon yy, which is tau yy by E. Similarly, you can write for the case where you apply normal stress along z direction. Now, let us analyze a particular row. What we have seen is column wise. Let us analyze one particular row. Let us take the first row. Okay. Now, what is significance of the first row? It says normal strain as the row heading. It tells the contribution to normal strain because of normal stress in x direction, normal stress in y direction, normal stress in z direction. And this is what we have seen in the previous slide, and that is what is shown here. We have seen the first 2 terms here. Look at the first row. In the first row, the first column entry is tau xx by E, second column entry is minus nu tau yy by E, and because it is 3 dimensional case, you have one more entry minus nu tau zz by E. Okay. The significance of the different terms in the first row are contribution to normal strain along x direction because of normal stress in x direction, normal stress in y direction, normal stress in z direction. Okay. So, if you sum up all of them, you get the normal strain in x direction because of normal stresses in x, y and z direction. That is the significance. That is what we have seen in the previous slide. Considering only xx and yy, this table of course generalizes for zz also. Okay. So, what is this table about? We can discuss both column wise and row wise. The entries in the column are the effect of stress in one direction on strain in 3 directions. If you consider row wise, it is effect of stress in 3 directions on strain in one direction. Okay. So, similarly, you can discuss for epsilon yy and epsilon zz. Okay. Because all the relationships are linear, we just superimpose the effects of the 3 normal stresses. Okay. What we have written, first column is because of normal stress in x direction, second because of normal stress in y direction, similarly normal stress in z direction, and each individually tells you what is the normal strain in the x direction. Now, we are just going to add. When is it possible? Because they are linear relationship, and that is why we are able to just add them, or more formally we can say superimpose. Okay. So, that is why since all relations are linear, superimpose effects of tau xx, tau yy, tau zz. That is the meaning of this addition. Ni epsilon xx, this epsilon xx represents the normal strain taking into account effect of tau xx, tau yy and tau zz. All 3 normal stresses are effect of all 3 normal stresses are taken into account, and this addition is possible or superposition is possible because the relationships are linear. Now, so what I have done is added the first added the entries in the first row tau xx by E and then minus nu into tau yy by E and then minus nu tau zz by E. When you look at that expression, what should come to your mind, the way in which we should interpret that is, the first term represents the effect on normal strain due to normal stress in the same direction. Other two, the effect on normal strain because of normal stress in the two other perpendicular directions. Okay. That is what you should understand. Okay. So, the effect of normal stress in all three directions are brought into this equation, okay, or summed up in this equation. Okay. Of course, 1 by E is common, you can write this expression for epsilon xx as 1 by E and then tau xx minus nu into tau yy plus tau zz. Okay. Similarly, you can write for other directions as well, which means I am summing up the entries in the second row and summing up entries in the third row as well. So, second row tells the normal strain in y direction because of once again 3 normal stresses, and third row tells normal strain in z direction because of normal stress in 3 directions. Okay. So far we discussed about normal strain. So, now let us discuss about shear strain. Shear strain, we introduced the shear modulus based on the linear relationship between tau xy and gamma xy. Okay. We said tau xy versus gamma xy is linear and the proportionality constant is shear modulus. Same expression is written, but for shear strain. We have the previous slide we wrote expressions for the normal strain. Now, we are going to write expressions for the shear strain. So, the shear strain in the xy plane gamma xy is equal to tau xy by g. Now, remember we discussed about the strain tensor, where the components were epsilon xx, epsilon yy, and then epsilon xy was the component of the strain tensor. So, we can write an expression for epsilon xy, which is the component of strain tensor. We have seen that epsilon xy is gamma xy by 2. So, epsilon xy is equal to tau xy by 2g. Okay. Remember, the graph is between tau xy and gamma xy, not epsilon xy. Please pay attention to that. It is tau xy and gamma xy and not epsilon xy. Why is that? What we experimentally measure is gamma xy, not epsilon xy. Okay. So, the G connects tau xy and gamma xy and not tau xy and epsilon xy. Okay. Why epsilon xy? Why are we interested in epsilon xy? Because that is the component which appears in the strain tensor, and epsilon xy is related to gamma xy as epsilon xy is equal to gamma xy by 2. Okay. So, we can relate gamma xy and tau xy also, which is tau xy by 2g. Okay. Similarly, we can write expressions for gamma yz as tau yz by g. You can write expression for epsilon yz also as tau yz by 2g. Similarly, for gamma zx also. Okay. Now, we should note one difference between the way in which we wrote normal strains and then shear strain. Okay. Now, when we had an expression for epsilon xx, okay, on the right hand side we took into effect of tau xx, tau yy and tau zz. Okay. So, normal stresses acting on along x direction, y direction, z direction had effect on normal strain along x direction. But now look at the expression for shear strain. Gamma xy is written to be depending only on tau xy, not on tau yz or tau zx. Okay. So, one quick rough way of understanding is that you have a plate, you apply a shearing stress, the change in angle depends on this shear stress alone. this shear strain along xy plane is not going to depend on shear stress along yz plane and zx plane. So, that way these relationships are, I would say, simpler compared to the normal compared to the relationships for normal strain. They just depend on the shear stress in that plane only. Okay. So, any shear strain component is proportional to only corresponding shear stress component, okay, and independent of normal stress components also. We have not even considered the effect of normal stress also. Okay. So, any shear strain component, let us say gamma xy, is proportional to only corresponding shear stress component, which is tau xy, and independent of normal stress components. We have not considered dependency of gamma xy on, let us say, tau xx, tau yy, tau zz. We are taking gamma xy to depend only on tau xy only. That way these relationships are like a standalone relationship. Straight away you can get shear strain in terms of shear stress, and later on you will express shear stress in terms of shear strain also. Okay, so those are the stress tensor and the strain tensor. So, those are the assumptions which I have discussed: homogeneous, isotropic, linear, elastic solid. We can now summarize all the relationships which I have discussed so far for normal strain and shear strain. Okay. So, we have seen this expression for normal strain along x axis. Analogously, we can write an expression for normal strain along y axis, similarly normal strain along z axis, and we can also write expression for shear strain epsilon xy, epsilon yz, and then epsilon zx. Okay. So, what is that we have done? We have written relationships for the diagonal components of strain tensor epsilon xx, epsilon yy, epsilon zz, the normal strains. We have also written expression for the 3 off diagonal strain tensor components, namely epsilon xy. We have also written expression for the off diagonal elements, namely epsilon xy, epsilon yz, and then epsilon zx. So, how did we write? We wrote them in terms of the components of the stress tensor. Okay. Okay. So, 6 scalar relations, okay, between 6 independent stress and strain components. Remember, we discussed the stress tensor as 9 components, but only 6 are independent. Similarly, for the strain tensor, there are 9 components, but only 6 are independent. Epsilon xy is equal to epsilon yx. We have not even shown epsilon yx here, because we have taken epsilon yx to be equal to epsilon xy. So, 6 independent stress tensor components, 6 independent strain tensor components, and there are 6 scalar relations between the 6 independent stress and strain components, and that is the 3-dimensional form of Hooke's law. Where is Hooke's law known to you? That is here, epsilon xx is equal to tau xx by E. That is where what we already know, very well known to us, is one simplified form of what we have discussed so far. Okay. We have really discussed a more general form of Hooke's law, a 3-dimensional version of Hooke's law. Even what we have discussed is under this assumption: homogeneous, isotropic, linear, elastic. Okay. What we already know, very well known to us, most of us, is the Hooke's law given by epsilon xx is equal to 1 by E tau xx. What we have seen is a more generic version which is applicable for a 3-dimensional case. Okay. And remember, the Hooke's law is written for epsilon xy and not for gamma xy. Why is it? Because epsilon xy is the component of the strain tensor, not gamma xy. Okay. I have not written for gamma xy is equal to tau xy by g. I have written as epsilon xy equal to tau xy by 2g. The reason is we are writing expressions for components of strain tensor in terms of components of stress tensor. Okay. That is why, but the original experimentation is between tau xy and gamma xy, okay, because that is from experiment we measure straight away change in angle, okay. That is why the x axis there is gamma xy, but we need relationship for epsilon xy, okay. That has to be kept in mind. Okay. Now, let us summarize all the equations here which I have listed in the previous slide. The left hand side shows expressions for the normal strains, and the right hand side shows expressions for the shear strains. Okay. Now, if you look at the equations and even if you look at the way in which you have discussed, there are three material properties. What are they? The Young's modulus E, and then the shear modulus G, the Poisson ratio. Okay. There are three material properties, okay, but only two of them are independent. One depends on the other. One of them depends on the other. You cannot, there cannot be three independent material properties. We can show that there is a relationship between E, nu and G, resulting in only two independent material properties, okay. And that is our next objective. What is the relationship between the three material properties? Okay. So, we will derive the relationship between three material properties, because the Hooke's law under these assumptions can have only two independent material properties. Okay. So, we are proceeding towards deriving a relationship between E, G and nu.